So BinarX is all about building a payload. That's the part of a spacecraft that actually carries out the mission. So while our Binar bus takes care of stuff like power and navigation and communications with the ground, your payload is the bit that's actually going to be answering an interesting question. Now, there's a whole process to figuring out what question we want to ask when we're up there. That's our mission concept review that's also coming up. But we also need to figure out how to answer it, how to actually put our payload system together. And the best way to learn how to do that is to actually build one. So we're going to build our very first payload system together. And to help me out, I'm going to go have a chat to our payload engineer, Jacob.
All right, so Jacob, this is Jacob. Observe, Jacob. I am obviously not an engineer. Jacob very much is an engineer.
I think so.
So
that's what people have told me.
So we're going to build a little project. What are we building, actually? That's probably a good place to start, right?
Of course, yeah. So, I mean, physically what we're building a temperature sensor.
Right.
But as an overall concept, what we're building is the absolute basics for what you need for a payload in space.
Let's take a look at what that actually is going to look like if we wanted to make one as a little bit of a project.
Yeah, of course. We'll switch to the desk.
And we switch to the desk.
So as a block system, which we'll draw here, so we have our input. So this is our battery. And that outputs our 9 volts. And that goes into our LDO. And that is what converts our 9 volts into our operating voltage. And then from this block, we have 1 bit of operating voltage that will go out to our microcontroller, and 1 bit of operating voltage that will go to our sensor, because both of them need to be powered, and 1 bit of operating voltage here that will go to our signal conditioning block, which is our bar graph driver. And then what happens is our sensor measures the temperature from the environment and then outputs a voltage. And that voltage changes depending on what the temperature is into the microcontroller. The microcontroller reads that from the sensor. And then the output from the microcontroller is a scaled voltage, which goes into our signal conditioning, our bar graph driver. And then the output from this block goes to our bar graph itself. And then that is where we can look at that. So we can look at that with our eyes, and we can see what the temperature is based off of what this is measuring. And then the final part of the system is some way to tell it when to run, tell it when to take readings. So for that, we have a switch, and that switch goes into the microcontroller, which you can press with your finger. And when you press the switch, the microcontroller takes a reading from the sensor and then outputs it to the bar graph, which we can see.
How would this system sort of change once we put it in space?
That is actually a really good question. So a couple of things to think about once we actually put this system into space. If we wanted to take this exact system and put it into the satellite so that it runs in space exactly as is, there's a couple of things that we're changing, which are primarily on the outside of this whole section. So this middle part here, inside the dots, that stays exactly the same. So this, the way we're going to be setting up this, you could put this straight into the spacecraft and it would be identical. The primary changes are the way that this system interacts with the environment, because if you think about when you're orbiting in space, obviously, or unless you've got really long arms, you're not going to be able to press the button to turn it on. So this switch to turn it on changes, and then, I mean, I don't know about you, but I struggle to see satellites operating in space with my eyes.
Especially
so
one as little as ours, yeah.
Yeah. So I'm
just about to see the space station, but you can't.
Yeah, the space station.
CubeSat.
Space station looks like a dot of light, and the CubeSat is a lot smaller than the space station. So if we would leave this the same, we're going to struggle to be able to see the LEDs on it.
Okay.
So that also needs to change, because we can't tell it to turn on because we can't press the button, and we can't see the output because we can't see the satellite. And the third thing that changes is the battery, because while we have a 9-volt battery on the device here, in the satellite we don't have a 9-volt battery, and we don't need to put a battery in the payload because the satellite will power this itself. So that battery voltage will come from the satellite. And the blocks themselves are all the same across, like every payload has the fundamental blocks that are a part of it. The actual implementation for how the block is created in terms of a circuit can change, and usually does change, but fundamentally the blocks are always the same.
Right.
So in a payload you have to have some way of sensing data. So you have what's called a sensor.
Right, because otherwise what's the point, right? We can send a
Exactly,
thing to space,
exactly.
but if we can't get any information back, what's the point of having sent it up there?
Yeah. Fundamentally what a sensor is doing is it's converting data from the environment, in this case temperature, or it could be light on a sensor, or it could be radiation, it could be lots of different things. You convert data from the environment into an electrical signal, and then connected to that sensor, controlling the sensor, hence why it's called a microcontroller, we have the microcontroller. That is the sort of the central block of your payload, and that's the brains. So that is the part of the block that runs your software. So in the case of the temperature sensor, that is the part that records the temperature of the environment from the temperature sensor itself. It measures the voltage that it's outputting.
Yeah.
And then it outputs a different voltage, which is the data that it's outputting, that you've measured.
Right.
You could have it output an analog voltage, which is proportional to the voltage that it's reading, or you could have it output like a digital signal where it turns on or off when it goes above a certain temperature.
Right.
Lots of different things. It's really up to you and up to your imagination what you want to do.
Yeah, and kind of up to what you want to do with the data as well.
Exactly.
Right?
Yeah.
If you just want to know whether it's above or below a particular temperature, you could use a yes/no. If you want to be able to measure it, we can use a voltage.
Yeah.
And I'm sure there's more complicated things you can do with it.
Oh,
as well.
there's lots and lots of stuff you can do with it, but primarily, the decision for what you do with it is made from the science that you want to do with your payload.
Right.
And then, like we were saying, the output from the signal conditioning block goes to some way to visualize the data. And I guess the second to last block we've got in the system is some way to control your payload. In the case of a payload, it will be an input from the spacecraft itself, telling it when it can turn on and off, because the spacecraft overall will govern how much power is available to use from the batteries.
Right.
And if the spacecraft says there's not enough power in the batteries, I need you to turn off, then the payload needs to turn off.
It needs to do what it's told, yeah.
And the final block, as sort of alluded to, is the power. So the payload will connect to the spacecraft's batteries, and that's where it will get its power from. We need some way to convert the voltage from the batteries into a voltage that is like a voltage level that we can operate on and we can use, because the microcontroller that we have runs on a lot lower voltage than the batteries will output.
Yep.
The batteries in the solar panels will produce around about 8 volts at the maximum, and that's far too high for most microcontrollers. That will just burn them out immediately.
Cool.
So what we have is the power conversion block, which will either lower the voltage in the case of running our microcontroller, or sometimes it will increase the voltage in case of running really high voltage sensors.
Yep. Cool. We're going to try and make, I guess, a really simple version of this system. What parts are we using?
Of course. So for the battery, as we mentioned, 9 volts sort of hints at the fact that we're going to be using a 9-volt battery. So that is our power supply. And then to connect the 9-volt battery to the rest of the circuit, we need the 9-volt battery clip. So that will go on, just allows us to use the plug terminals to connect to the breadboard. And then from that, the first stage, which is powering everything as we discussed before, is the LDO. So that is this little guy here. And in addition to that, we need 2 capacitors, which are these little guys.
Okay, so what is this guy?
So an LDO is an acronym. It stands for Low Dropout Voltage Regulator. So VG is not on the end of it. It's just known as an LDO. And what it does is it takes a higher voltage on the input and then converts that to a lower voltage on the output. So the output for that will always be 5 volts.
Okay.
As long as the input is above the dropout voltage.
Right.
So the fact that we're putting in 9 volts is more than enough, and that will output 5 volts.
Cool.
And that allows us to set a fixed voltage for the system. So if we were to just power this off of a battery, for starters, you can't really get a battery that produces 5 volts. In addition to that, as the battery discharges, the voltage goes lower. And you'll see that's exactly the same as the way it works in the satellite. As the satellite battery is discharged, the voltage goes lower there as well.
Right.
And what we need is basically to take that voltage and then to convert that into one steady state voltage that we know is going to be the same voltage all the time. So the next part is the temperature sensor. So that looks exactly the same as the LDO. It is a different part. They do have different writing on them. The temperature sensor has 3 legs on it. One leg is for the power that comes in.
Yep.
One leg is for the ground, which is connected to the common circuit ground.
Yep.
Which is like where the battery negative terminal goes. And one leg is the voltage output. So as long as this has got power, it will adjust the voltage that's coming out of it to match the temperature that it's reading.
Yep. And where do we find out what temperature maps to which voltage?
That is in the part data sheet. That is also where you will find which pin does what. That's where you'll find all the information about the part. These data sheets are very, very good, very useful. And I would thoroughly recommend if you're going to be doing something like this, read the data sheet and have a look at what it says in there. And that will tell you whether the part's going to work and it's going to operate the way you expect it to. And in addition to that, then it will, if the part does work the way you intend it to, it'll give you the values that you need for setting it up. So when we mentioned that we've got the two capacitors here for the LDO, these capacitor sizes were outlined in the data sheet.
Yeah.
So the next part after the temperature sensor is the microcontroller. And now this is definitely micro because this is the size of it. That is our whole processor that will control all of the inputs and outputs and all of the functions. And that's where all your software goes on. And that controls the entire system.
It's kind of adorable. Can I?
Of course.
Oh, it's so weeny.
Pretty powerful though. So if you want an idea of how power has changed over the years, the Apollo guidance computer that was used in the Apollo 11 moon landing spacecraft had the equivalent of 2 at-tiny's worth of memory.
And how much did it weigh?
It weighed about 30 kilograms.
Okay.
So, and that probably weighs maybe half a gram, which I think is it's quite cool. So the next block we have is the signal conditioning block. Now this chip we've got here, quite a bit bigger. That is because we have a number of output registers to talk to the LED bar graph. And this chip takes in an analog voltage, which will generate from the microcontroller, and turns the outputs on and off. So basically it turns it into what's called a digital signal. And a digital signal compared to an analog signal is like a varying voltage. So we have anywhere from 0 to 5. For any of the gamers that are watching, it's like an analog joystick. You can have an input where it's a whole range as you move the joystick around. A digital input or an output is either on or off. It's like a light switch or it's like the face buttons on the controller. In addition to that, we have to be able to set the range that the signal conditioning chip operates at, and for that we've got 2 resistors.
How do we know which resistors to use?
Again, the resistors that we select come from the chip data sheet. Nice. The data sheet will tell us exactly what to use. The 10 digital outputs from the signal conditioning circuit go to the voltage level indicator, or the LED bar graph, which is this part. And what this part has, on the bottom at least, it has a little 20 pins. And 10 of those pins are the inputs to the LEDs, and 10 of them the outputs from the LEDs. And the inputs from this all join together where the power comes in. The outputs go to this chip, and this chip will turn them on and off. And then the final part we have in the circuit is the way we can interact with it. It is the human signal input to tell it when to take readings, and that is the switch. Everyone loves pressing switches.
Yeah, that's very satisfying, very clicky. That switch goes here.
So that is all of the parts we need to make our equivalent to a payload. So as we were saying, if we wanted to convert this into a payload that could operate on the spacecraft, the only thing we would need to do is just remove these parts. This center block that we've got here, that's still exactly the same. I think that's it.
I think that's it.
Yeah. Let's put it this way.
Very neat. I love the little like. That was a nice little.
I knew that was going to be it. Yeah. I was like, I've got enough artistic flair that I know this is going to be good. Yeah.
So that's the challenge. If you want to race ahead, if you've got an Arduino and a sound sensor or a Raspberry Pi and a light detector, and you reckon you've got this down, go for it. If you don't, that's okay, because neither do I. I'm going to have a go at this project as well. And if you want to follow along with us as we make our test project, there is a parts list to do exactly what we are doing in the description. Can't wait to see what you make.